This comparison shows the difference between a hand-drawn reaction cycle and a mathematically symmetrical elliptical diagram. While both represent the same chemistry, the right version uses geometric precision to improve visual communication. In modern labs, chemical information is increasingly integrated with AI-driven discovery platforms. To predict interactions, the digital data must be recorded with high precision. We can achieve this standard by moving away from freehand drawing. With professional shortcuts, we can generate automated structures and manipulate arrow geometry into a perfect ellipse. Mastering these techniques allows you to produce diagrams that meet publication standards while ensuring your chemical data is formatted correctly for digital research environments. The first step is addressing the canvas scaling. Beginner drawings often suffer from disproportionately tiny atom labels set against oversized bonds, which makes complex cycles difficult to read. To fix this, navigate to the File menu, select Apply Document Settings, and choose ACS Document 1996. This template ensures that every atom and bond you draw is scaled correctly from the start, maintaining a professional ratio across your entire document. Applying these industry standard settings before you begin prevents the formatting and scaling errors that often accumulate during a long drawing session. With the canvas set, we need to add our reaction components. Drawing complex catalyst from scratch is time-consuming and increases the likelihood of a human error in the chemical structure. You can automate this using the Convert Name to Structure tool. For common reagents like bromobenzene, typing the name allows the software to generate the structure for you. For more complex molecules, researchers use the SMILE string, a text-based chemical identifier that represents molecular structures in a format machines can easily parse. You can find these strings on databases like PubChem. Once you copy the isomeric SMILE string, go to the Edit menu in ChemDraw, select Paste Special, and click Smiles. The software immediately renders a flawlessly formatted structure. Because this comes directly from a verified database, the chemical data is accurate and ready for AI integration. Using automated identifiers like SMILES ensures that your foundational chemical data is free from the manual errors common in hand-drawn structures. Now we can construct the cycle. Most diagrams look uneven because the user draws several separate curved arrows, which are difficult to align manually. Instead, draw a single line with the curved arrow tool, dragging the ends to form a closed circle. Hold Shift and drag the boundaries to distort it into a smooth ellipse. Then adjust the curvature's radius using the central handle to fit your pathway. Starting with a single master shape, rather than piecing together fragments, guarantees that the final cycle will have total geometric symmetry. Place your starting catalyst at the apex of the ellipse. For accurate chemical typography, use the F9 key for subscripts and F10 for superscripts. Duplicate your master ellipse and place it directly on top. Drag the endpoints back to create the first segment. Repeat this process to carve uniform gaps around the perimeter, ensuring every arrow follows the exact same geometric curve. Now, move your previously generated SMILE structures into these gaps. Because the arrows were carved from a single master shape, the reagents will align perfectly with the pathway. If you need to combine separate molecular pieces, select M and use the Ctrl-J shortcut to join the structures into a single unit. To complete the bottom of the cycle, you can use the Flip Horizontal command on your arrow segments to maintain a consistent flow for the reaction. This method of duplication and cropping mathematically enforces alignment, removing the need for freehand adjustments and ensuring a professional finish. This final elliptical catalytic cycle is a precise representation of the chemical process, formatted to meet the requirements of modern digital frameworks. This level of precision provides human readers with immediate visual clarity and ensures that the underlying structural data is formatted for use in digital repositories and AI models. By combining standardized document settings with automated structure generation, you bridge the gap between human chemical intuition and the rigid data requirements of the modern lab. Applying these technical standards ensures that your work is not only visually professional, but also serves as a reliable digital record of your research.